There's one last thing we need to say about this topic before we leave page 3, and that is the difference between dependent and independent events. We just got done looking at the tree diagram for drawing the balls out of a box, and we noticed that the probability of B2 is affected by our knowledge of what came ahead of it. So what happened on the first draw certainly does influence our judgment about how likely, say, blue on the second draw would be. In other words, we have computed this. The probability of B2, we just did that, that's 1/2. The probability of B2, say, given B1, that we've computed before. It's on our tree diagram. B2 given B1, that's 2/5. So in other words, knowing that we got a blue on the first does in fact affect the likelihood that we'll get a blue on the second draw. Now, we could contrast this with, say, the coin flipping experiment we had at the top of page 3. If we look back there, we see that the probability of heads on the second flip is 1/2, whether we got a head or a tail on the first flip. So that is to say, the probability of heads on the second flip is 1/2. It's also true that the probability of heads on the second, given, say, a tail on the first, is equal to 1/2. In this case, these two probabilities are equal. That's an H right there. Head on the second. In this case, these two are equal. The additional information that there was a tail on the first flip is of no help in estimating the likelihood that we'll get a head on the second. On the other hand, the information that we got a blue on the first draw is of value in determining the likelihood that we'll get a blue on the second draw. In this case here, we say that B1 and B2 are dependent. And in this case here, we say that T1 and H2 are independent. In general, the rule is this. If we have two events, A and B, in mind, if the probability that B occurs, given that A occurs, is just the same as the probability of B without any further information, then we say that A and B are independent. One does not influence the likelihood that the other will occur. The other possibility is that the probability of B, given the information that A has occurred, is not the same as the probability of B without any conditions attached. If these are not equal, then we say that A and B are dependent. This makes a lot of sense if we think about the physical situation. In the case of balls in a box, where we take out two balls in succession without replacement, there is a kind of memory to this apparatus. If I take out a red but not a blue, then the next draw will be shifted slightly in favor of getting a blue because there'll be more blues than reds in the box. In the same way, if I drew out a blue on the first draw, then it's slightly more likely that I'll get a red on the second rather than a blue. In the case of flipping a coin, though, there is no memory built into the apparatus that we're using. The coin does not care what happened on the previous flip, or for that matter, on the previous 100 flips. Each time you flip a fair coin, the probability of head and the probability of tail are fixed at 1/2. So when we're talking about flipping coins, it doesn't surprise us that these kind of events, what happens on the first flip and what happens on the second, are independent. The coin has no memory. But in the case of drawing the balls out of the box, even though the inanimate objects can't actually remember, there are different physical configurations based on whether we get a blue or a red on the first draw. And therefore, what happens on the first draw does influence the likelihood of what happens on the second. In that case, we say they are dependent. If one does not influence the other, we say they are independent. And that completes our work for page 3.